Good afternoon, everybody, once again. After a very heavy lunch, I hope there won't be a larger number of people dozing off. I hope it was interesting, and the energy that you got from the first session should be further increased after this session, I'm sure. So, actually, we are talking a lot of technologies, but without really understanding the very basics of from where we started thinking differently, I think we will not get a very clear or a comprehensive picture. So to tell us, in fact, more on the basics, the introduction to thermal power systems, we have with us the expert for the afternoon. Before that, just to, again re-jog your memory, coal-based thermal power has driven much of India's power sector growth over the past 3 decades. Power sector consumes about 80% of the coal produced in the country, and as the demand for electricity is expected to rise dramatically over the next decade, coal will continue to be the dominant energy source. The total installed capacity of the country is currently estimated at 205.34 gigawatts, and of this, around 137 gigawatts or 66.5% of the total installed capacity is based on thermal power. And coal-based power plants account for 85% of the thermal power. So far, subcritical pulverized coal-based combustion power plants manufactured by BHEL have been the backbone of India's coal power sector. Nowadays, we have just seen, as Dr. Sipana had given you some few thought-provoking slides, supercritical and ultra-supercritical boilers are also becoming more relevant, and it shall be installed. From now on, the installation of coal power plants is going to be dominated by these two technologies in the 12th five-year plan onwards. So, I'm glad once again to introduce to you the speaker for the session, Mr. V. Sitaraman, Manager Boiler Performance and Proposals, BPP Department. He has over 3 decades of rich experience and expertise in carrying out boiler design and performance engineering calculations for industry and utility steam generators, both subcritical as well as supercritical units. He has also had the opportunity to undergo intensive training in Alstom, Windsor for once-through supercritical boiler performance design. His areas of interest include thermal design, coal and oil combustion technologies, etc. So let me just hand over the floor to Mr. Sitaraman.
Good afternoon. As Madam said, after a heavy lunch, it's my challenge to keep you all not to sleep. So, keeping that in mind, I will make this session, I hope, very lively. Okay? See, this is to give an introduction about the thermal systems. And the picture shows the second augmentation of BHEL manufacturing unit. This is the second phase of manufacturing unit. This is a 100% augmentation what has been there earlier. So the development has gone to that level of making 20,000 megawatt. 15,000 to 20,000 we are proceeding towards that capacity. Now, if you take the options in power generation, it is hydro, thermal, nuclear and non-conventional, everybody knows. And coming to the thermal power plants, which is our topic today, we have got steam power plants. That is, it contains of BTG, boiler, turbine, of course, boiler turbine and other systems which are related to that. We will call it as BOP, okay, balance of plant. And then the gas turbine based power plants. And coming to this boiler and turbine, we are having oil, coal and gas fired. As Madam said that most of the units are working on coal based. Now we are not having the thermal power plants with the oil because If we go with the combined cycle demonstration, combined cycle plant, the oil fired boiler emissions will be more. Mostly the fired boilers, that is PF fired, pulverized fuel fired boilers, will have coal as the main fuel. And this is pulverized fuel you can have, fluid technology you can have. Today I am going to mostly explain the pulverized fuel technology. Now, out of the areas in BHEL, we have got sectors, power sector, thermal, hydro, gas. The same thing is given in the BHEL's style of working, that is all these product profiles are shown here. So, out of the installed capacity of 1,80,413 megawatt as on March 2012, the capacity of BHEL is around 75%. It's around 75%. Now these are all the list showing that more than 36 numbers of boilers we have supplied overseas. This is to show that the technology what is available today with us. Now this slide indicates as the trend in the cycle parameters for a boiler. You all know the Rankine cycle, which I am going to just explain in the coming slides. When the pressure and the temperature of the boiler increases, your efficiency increases. That is the work done. The work done will keep the same level of megawatt. Pressure cycle rate increases. See, earlier in long back when we started in 63, the pressure cycles were something like 96 kg pressure, and to that level now it has gone to 256 in the superheater outlet. That the turbine, when the turbine is operating at higher pressures and higher pressures, you will have the cycle efficiency that will be increased. So you can have a better cycle efficiency by which you can fire less. So the emission levels will come down. Now the idea is to have, when you are going for 660 megawatt, 700 megawatt, 800 megawatt, these are supercritical cycles. Any pressure which is more than 221 bar, that is supercritical cycle, when you work on that, your efficiency will increase. That I will explain you in the coming slides. Now this is the heat balance diagram of a 270 megawatt subcritical boiler. That is what is that actually there in the power plant. When you say thermal power plant, you should know what is there actually. Now we have got a boiler. The boiler gives steam at the rated steam flow and the pressure and the temperature to the turbine. So the turbine is high pressure turbine, intermediate pressure turbine and low pressure turbine. So you are sending the steam from the boiler outlet through the critical pipings. We call it critical pipings because these are the important pipings which are taking high pressure pipings, which are taking the steam from boiler to the turbine. Say, supposing I need a pressure at this point at turbine, some 160 at I require. Then the losses also should be included into that pipeline. Then when the pressure required at this point should be decided. Okay, actually this is 160 is at boiler outlet. When you see here it will be 150 at a cycle. So you have got some 8 to 9 kg pressure drop required for the cycles, power cycle. Now this boiler, when the steam goes here, it is expanded in the high pressure turbine. Then it comes down, okay, and then it is reheated in the reheater cycle. When it is expanding in the high pressure turbine, it is losing its pressure as well as the temperature is also coming down. As you know, that is incompressible liquid and pressure cannot be increased. We are increasing the temperature in the reheat cycle. So when you increase the temperature in the reheat cycle, that too is taken care in the boiler, inside the boiler. This is the reheater. Then it goes to the IPT, intermediate pressure turbine. That also it expands and does work, and then it is going to the LPT turbine finally. So okay, from the LPT it is coming down to the condenser, get condensed. After this, when I talk about this is a boiler, these are all completely turbine. After that, these things, that is condenser, it is condensate extraction pump. That is, you have to condense it first. Whatever is there in the LPT, it has to be condensed in the condenser. Then there is a extraction pump. for the condensate. Then that is sent to the low pressure heaters. As you know, the regenerative Rankine cycle, which will be explained in the next slide, coming slide. So these are all the low pressure heaters. Then after that, you have got a de-aerator. You have to de-aerate because if oxygen is there or aeration is there, it will corrode the things totally. So you have to de-aerate it. After de-aeration, you have the feed pumps, boiler feed pump, which will develop the maximum pressure that is required for the boiler inlet. This will only develop. That is called boiler feed pump. So this is, after this, whatever you get is a high pressure line. Then this is a high pressure heater you have got. That also heats. These heaters are taking the bread steam from the turbine. So you are breathing some steam from these turbines and giving it for heating these heaters. Then this is going back to through the economizer, it will go to the boiler. This is a total cycle. In this, you should understand that if you say boiler, this is turbine, this is called BTG, boiler and turbine package, including the piping. The other areas are called balance of plant. In this balance of plant, there are certain things that are left, like you have got other systems like coal handling, ash handling, all these things. All these things are put together and they are called as thermal system or thermal power plant system. For a thermal power plant, you need all these things. And the portion of boiler, if you can say, it is something like 30 to 35%. Okay. Now, this is just elaborating the earlier one, whatever you saw. The boiler alone, they are just elaborating. Boiler, what happens? So, there is a drum. The water comes down, getting heated up with the evaporator, goes back to the drum. From there, you are taking the steam down and then heating it in the superheaters, giving to the HP turbines. From the HP turbines, you are taking it back and reheating it, whatever I have told you. This is given in schematic diagram. Then it is going to the IPT. These things are called a high pressure stop valve and control valve. So this has to control the temperature that is going into the turbine at various loads. And of course, whatever we saw, that condenser and all the things are here. Same thing, LP heaters, HP heaters, is given in an elaborated view. Coming to the Rankine cycle, this is the basis for your any thermal power plant or boiler. Now, what is happening in the Rankine cycle? See, when you take from 3 to 3 dash, it's a T-bar diagram. See, the boiler feed pump, whatever we saw, it is raising the pressure from PD to P1. Okay? The total pressure is raised here. Now, 3 to 4, this is heating the feed heaters and economizer. So, this is sensible heat addition. Sensible heat addition is taking place in the economizer as well as the evaporator. Then, 4 to 1, complete heating in boiler. This is latent heat addition. Complete latent heat addition. So, sensible heat plus latent heat is taking up here. And then the work is done in the turbine. What is that? Adiabatic expansion. So, complete, there is no heat transfer. Adiabatic expansion takes place from T1 to 1 to 2. The work is done. Then you are bringing it back to the P2 to 3. So, heat reduction in the condenser is taking place. Then the cycle continues. Now, this is the basis, the basic Rankine cycle. What is being used in the power plant is slightly advanced. Now, this is the reheat Rankine's regenerative reheat Rankine cycle, or you can call it modified regenerative reheat Rankine cycle. Now, you could see that. See, this is the evaporation line completely. So when you are taking it, now there is a regeneration taking place in this area. Whatever LP heaters and HP heaters you are using, you are introducing some amount of heat from the blade steam by increasing the efficiency, that is increasing the work done. And then you have got the latent heat addition. When you superheat it to the top, up to 540 degrees centigrade for some critical boilers. Okay, when you superheat it to 540 degrees centigrade, then you are expanding it in the turbine. Again, reheating it. By reheating, this area of work done is increasing. You are doing more work in the turbine. So, then it is coming back and it is condensed. The back pressure is back. When you have the back pressure turbine, it is condensed in the vacuum. So, it is less than atmosphere. In the vacuum, you are 0.2 kg or 0.25 kg, you are expanding it in the bottom. And then it is coming back. So, the work done is this. So this is by this Rankine cycle, when you have a regenerative, these things are regenerative cycles. Regenerative and superheat reheat cycle, you have a better efficiency in the Rankine cycle. How is that is being done in a boiler? That we can have in the next slides. Now, what is happening in a boiler? When you say it's a simple, say a subcritical 210 megawatt boiler, 210 or 250 megawatt boiler, this a coal-fired boiler, which has got this. We have got some 4 or 5 designs of boiler by configuration. To explain you in simple, this is one type of major type of boiler which we normally use. This is called a 2-pass conventional type boiler. So 2-pass boiler, there is a 1 pass is this one, this is a second pass. So this is the horizontal pass, and these valves, water valves, okay, and because since I have most of them are from the college students, I would like to explain them, because it is not the thing which you are studying in the book. And the arrangement of the boiler, when you see, this is the height 53.34 meters from the ground. It is something like 170 feet. The height of the Srirangam Gopuram is something like 200 feet, 210 or 220 feet. Your Rockford is 286 feet. So something like 170 feet height, you will have the drum itself for a 210 megawatt boiler. When it goes to the 660 megawatt boiler, it will be something like 70 to 72 meters height. Okay. Now, these 4 walls are made by water walls, that is tubes. The tubes are welded in the membrane construction. It will be like a wall. And then this is the second pass. So these are all, this is the first one is called the Platon superheater. This is the final superheater. This is the drum, and your reheater section is here. This is low temperature superheater. That is 3 stages of superheater will be there. The first stage is low temperature, next one is Platon, third one is final superheater. So the water enters here, the economizer inlet, then it comes here, then it will go to the drum, and from the drum the water comes down, and it is just raising through the tubes of the water wall, raising up, and you have got fire. Fire is taking place here in the furnace. This is the furnace. So the heat is transferred from this furnace to the water walls, and then the water inside the tube becomes, it is absorbing the latent heat and becoming water plus steam. So the water steam mixture raises up, and the circulation is taking place because of the density difference. There's a density difference because the water inside this has more density, and the water inside the tubes are having lesser density because of the high temperature, and this denser water pushes it down to take it up. So that circulation takes place here. Once you have the steam at the top, then the steam is taken out through the tubes, and then it goes to the second pass, and it passes through all these stages of superheater, and you get the superheated steam. As you see from the Rankine cycle, the saturated steam is there after you take the latent heat. After the saturation, you are superheating it further. For example, if you have a 150 kg pressure, then your saturation temperature for that 150 kg pressure would be something in the order of 300 or 320 degrees centigrade. And from 320, you can raise up to 540 degrees centigrade. That is called superheating, further heating the steam. So the moisture in the steam will be completely driven out. Once it reaches the saturation line, then that itself your tightness fraction is 1. Further, you are making it almost equivalent to a gas. The property of steam says that when you are taking the steam much away from the saturation line, it will behave more or like a gas. Then you can have your turbine rolled based on that. So that is the thing. Now, in this context, I would like to show you one small circuit as an animation. Comes to that, and these are all the water walls, and in this case there's only a separator and you will not have a drum, And otherwise, all these superheaters, see, the bonding electrode, collecting electrode, and all that, I would like to show this arrangement. This is the funnel. So your duct will come and connect here. This is under erection, so the things are going on. So the gas will come in. It will go via these and big ducts inside. Sorry. In this, you will have inside some collecting electrodes and emitting electrodes. These emitting electrodes will emit corona, that is, very high voltage current will be passed through the emitting electrodes, which will be emitting corona discharge. What it will do, it will charge the particles which is suspended in the colloidal phase of the gas, so that the charged particles will get attracted towards the collecting electrodes, which are also negatively charged. So the positively charged particles will go to the negatively charged collecting electrodes, and after collection will be using a wrapping mechanism. They will wrap it and all the dust will fall down. So the collection efficiency we can achieve up to 99.7% or 99.6%. That is to get an outlet dust concentration which is dictated by the pollution control board. This equipment will be decided. The pollution control board, depending on the state, will decide what is the outlet concentration that is permitted in those areas. In certain states, it is even permitted only up to 50 mg per nanometer. In Tamil Nadu, if you say it is 100 mg per nanometer. So that it will be restricted to that level. And once you are not meeting that requirement, you will not be allowed to run the power plant. So this equipment is so important, and it will consume a lot of power, auxiliary power. So this is to give the overview of. So this is the generator. This is turbine bay. This is a turbine bay. This is a generator. This is a turbine. So you'll have set of turbines here. So this is to show how it will look like in the turbine bay. So when we see that the turbine means the imagination, whatever we have, we should have that we should imagine that how big it is and how people are managing it. There are power plants in the Western countries wherein only 3 or 4 people are managing the total power plant with so much of automation. And this is the whatever circuit I have told you to show you a typical steam and water circuit, how it will look like and all that. Now, I am coming from the drum for the superheater system. So once you there at the drum, then it will come to the other header. This is called roof inlet header. So you have got a first pass, second pass, those headers are clustered here actually. After going through the complicated circuits, it will come to the low temperature superheaters. So you have got 1, 2, 3 sets of superheaters for a 200 megawatt coil or a 250 megawatt coil. Then in between these two, there is one desuperheater. Why it is required? This is to control the temperature. We are telling that we have to give 540 degrees centigrade to the turbine. If the temperature increases, there will be a thermal shock. Temperature reduces also, there will be a problem. So, to control the temperature, you should have a spray mechanism, desuperheater spray mechanism, and you will have control valves and other accessories to control the desuperheater mechanism. It will be kept in between 2 superheater sections. So your surfaces will be made such that you will always get a higher temperature and not lower temperature. And whatever high temperature is there, that can be, you can spray. You cannot assure that you will be running a 500 megawatt boiler always at 500 megawatt. You may have to run it 400 or 300 megawatt. So that those things are called control ranges. So from 250 megawatt to 500 megawatt we can run a boiler. So if you are changing the megawatt rating, all our control system are to be, you should make sure that you are having all controls and other mechanisms to take care of these load changes and variables. So those things are possible. This is one temperature control mechanism. The same way for reheater also, in the subcritical boilers you will have a desuperheater in the entry to the reheater. But reheater temperature is controlled by other mechanism also called the tilt. In a tangential fired boiler, what is being supplied by BHEL, we have a tilt mechanism for the combustion systems. The combustion can tilt up and tilt down, total inbox. So the fire can be tilted up. The total firing, whatever is taking place, can be tilted up and can be tilted down. So that facility is available for regulating tangential firing. So that is also a mechanism for controlling your reheated temperature. And superheated temperature is controlled by your desuperheater. And you have got an economizer system, as you have seen here, inlet and outlet. You have got intermediate inlets. So there are other systems which are subsystems to support the boiler, support the pressure parts, okay, and to the firing systems, that is the burners and other accessories, and what are all the things required for burning. Supposing you have to ignite it, you should have an igniter. You have to fire with an LDO, then you should have a pumping and heating unit, pumping unit for LDO, HFO, heavy fuel oil, you have pumping and heating unit. Those are the subsystems that is also available in that. If you are very particular, and anybody is very particular about knowing some systems, you can always ask the questions in the question and answer session. I'll definitely answer you everything. But I am just covering the overall thermal plant with the specific mention to the boils. And this is the, that is the steam and water cycle. This is the air and gas path. When you take, this is the forced draft fan. So the forced draft fan, what it does, it is taking the air from the atmosphere, sending it through the steam coil air heater. This is a protection system to safeguard your air heaters. When the temperature is very low, you cannot have a very low air entering the air heater. As all of you know about the dew point and all that. When the sulfur is there, it will corrode your plates and all that. To avoid that, you should have a cold end protection. That is done by this steam coil air preheating. So the preheating is done by steam coil. But this is the main air heater. When it is going to the secondary air side, the gas is going through, and the gas will go through here. And then what is happening? The gas is coming out. Then it is going through the ESP. Fine. When the air is going through the secondary air side, this is getting heated up. So heated air, it is coming to the furnace through the wind box. That is the burning system. So when the burning system, I am splitting the air into two, primary air and secondary air. Why? Because in a pulverized fuel fired boiler, the pulverized fuel has to be transported to the furnace. The transporting can be done only through high pressure air. So what the air will do, the primary air, which is gaining heat from the air heater. The gaining heat, I can give you an example that from an atmospheric temperature of 30 degrees centigrade, say, it can even go up to 240 to 250 degrees centigrade. So that temperature, it will go, and then it will go to the mills, whatever we have shown. Before taking it or importing it, transporting it to the furnace, it will dry that. Whatever moisture available in the coal, it will be dried because of the heated air. Okay, how much is to be heated and how much it should dry, we can control it by mixing the coal there also. That's another technology available. And then from there, it will be transported through the coal pipes. These pipes will carry the coal plus air mixture into the furnace. So that is called coal burner, burning system. So between coal burners, you have got the air compartment, auxiliary air compartment, that is the secondary air. This secondary air is aiding the combustion. It is not enough if you send the coal inside. It has to get completely combust. It has to be completely burnt. For burning air, you give a supporting air that is called the secondary air. So the total portion of the air is divided into two. One is primary air, other is the secondary air. Once it is complete combustion takes place inside the furnace. After complete combustion, it has to be expelled. Now, to give an idea, the time at which the gas resides inside the furnace is approximately 2 seconds. When a particle comes in the furnace, it gets burnt, and when it comes to the bottom of the superheater, it is only 2 seconds. Before that, it should completely burn. to aid this, to help this, you are completely pulverizing the coal. When you pulverize a solid piece into small particles, the area that is available for combustion becomes more and it is completely burnt. And you have to supply the sufficient amount of oxygen also along with the ignition energy. The amount of oxygen you are supplying is dependent on your stoichiometric air requirement, whatever I said earlier, that is carbon, hydrogen, sulfur percentage of the fuel. Then you identify the oxygen requirement and you give some more exercise to that so that it is completely burnt. Now, you have to ensure the complete burning, otherwise you are losing. If you are sending some CO out of that, then you are losing the chemical energy from the fuel. The heat energy is not liberated. So the complete combustion should take place. After that, the gas, flue gas which is there, it is drawn by the ID fan. So it passes through the various sections. Before coming to furnace to air heater, you have got all these sections kept here. That is your superheaters, reheaters, your furnace, everything is there. So there will be a radiation heat transfer, convective heat transfer. So the radiation, the radiant heat transfer, the radiation will go to the evaporator. Some amount of the left out radiation will go to the superheaters, which is in the first pass exposing to the radiating surface. And then balance will be convective heat transfer. So all this heat gained by the gas is transferred to the superheaters and reheaters and economizer. And finally, the last heat recovery section is air heater. And after that, please remember, there is no heat recovery section from air outlet to the chimney. Then, why at all I should leave it at a temperature? Can I bring it down to 20 degree or 30 degree? You cannot, because you have got a sulfur dew point. Anything below 125 or 130 degrees centigrade, the presence of sulfur dioxide will get converted into SO3 and then you will have H2SO4. It will totally corrode the complete system beyond air heater. Even including the air heater, it will be corroded. So the ACET, average cold-in temperature, should be maintained for the respective fuel, depending on the sulfur content available. Fortunately, Indian fuels contain only 0.5% of sulfur approximately. Now, when you take some other countries, some other fuel will have 2.5 to 3%. And now we are going to get other statutory requirement that the SOx emissions, sulfur dioxide emissions, is going to be restricted in India also. It is there in other countries. Then if you want to reduce the SOx, where from it comes? See, it is from the fuel. The fuel, when you are going to fire the fuel, then you have to take that emissions also. Then you should have a flue gas desulfurization plant. If you are going to fire an imported coal with high sulfur, there is one more problem is that you have to install a desulfurization plant. Now the NOx, nitrogen oxides, these are all the pollutants. Not only the solid emissions. Solid emission is electrostatic precipitator. It is taking care of your solid emissions. That is, you are removing the particles. And the other things are NOx and SOx emissions. Sulfur oxides and the nitrogen oxides. Nitrogen oxides is from two phases. One is what is available in the fuel nitrogen. The other is the way in which you are burning it. How much amount of air you are using. And at what temperature you are allowing the burning to take place. By using the tangential fire system, you are doing the firing in various stages in vehicle boilers, by which your NOx, nitrogen oxide emission is controlled. The intensified heating will increase the nitrogen oxides. So there is another area of interest in which the combustion should be taken care of. So this is to give an overall idea about what are the important factors that are to be taken care in the thermal power plant. That too, in the thermal power plant, when you consider boiler, these are all the important systems: the steam and water circuit system, air and gas system, and fuel system, out of which the auxiliaries. So when you want to make a run of boiler very effectively, you have to minimize those losses. These losses are not something which can be, which is not coming from outside. So these are all from the fuel and the ambient conditions existing. And within that, you have to manage the situation. And it is not only designing a boiler, and it is designing a boiler very effectively. In today's scenario, if you could see that, to give an idea, if there is an efficiency fall, when you say an efficiency, thermal efficiency boiler, it is termed in terms of 1 minus losses. That is, whatever you are firing minus the losses. That is, there are many losses like dry gas loss, hydrogen moisture loss, and moisture in air loss. So unburned carbon loss, nil reject loss, like that. There are losses listed out in the code. When you make those losses, the customer will say that you have to follow the code, KSME PTC 4 or DSCM, something code you will specify, and everybody has to code following those code specifications. And when you are estimated for every 0.1% of variation in the efficiency, you may be even losing or gaining to the extent from 2 crores to 10 crores. For every 0.1% of efficiency, just imagine. This is the order of the day. You have to be very competitive with that. So your design and your operation, and if I am not proving that, I have to pay back the money. Whatever profit you are going to get, you have to pay back to the nose, or even more than that you have to pay back. The same way, the auxiliary power consumption, whatever power you are using for those auxiliaries, like your fans, ESP, mill, air heater, whatever is the thing, you are going to use, and you are going to spend some power from the power you are producing, there also you have to pay. It is called liquidated damages. Before making a design, before understanding the design of the power plant, this is the scenario of today. That also to be understood. So keeping that in mind, you will be very cautious on the basic parameters, whatever I said about the boiler. Okay. Now the range of the boilers, what BHEL is now making, is up to the 800 megawatt. We have got subcritical boilers and supercritical boilers. Now I will come to that. And let me take another 10 minutes and finish that. After 3:15, you can have your question and answer. Now, this is supercritical boilers. This is to give an introduction to that, because our first supercritical boiler is now being erected in Park site in Bihar, and will come into operation within another year, or maybe 7 or 8 months it will come into operation. This is that boiler. I was involved in that design completely. And when you see the parameters, it is 2120 tons per hour of steam has to be generated every hour. You have to generate 2020 tons of steam. And then the pressure is something like 255 kg per steam cut gauge pressure. And the reheater pressure is 54.65. And the temperature is, for superheater outlet, is 568 and reheater is 596. Now, to treat these temperatures, even now the materials are a challenge. Now to get materials from import materials, and there is one special material called Super 304H is being used in these boilers. It is more than a stainless steel. And the auxiliaries what we have used is 9 numbers of HP 1103 mills, whatever I have shown you mills like that. 9 numbers of mills we have used, and 4 numbers of heaters, 2 numbers of bigger FTP and ID fans each, and then the dust collector. It was not in the SG scope. Of course, it came to BHEL only through another system, and it is with BHEL. Now, what is a supercritical boiler? Anything which is operating above the critical pressure, say this steam generation process, as seen from here. This is the saturation line. This is saturation line, and this is a liquid line. This is the vapor line. This is the critical point. So anything which is operating above this critical point is called supercritical. So what is happening? Up to this range, you have to have latent heat addition for various pressures. When you go to that level, there is no latent heat addition. When you reach that temperature, the water flashes into steam. So the water flashes into steam without the addition of latent heat. To give further to that, if you see the T-pi curve, this is a Rankine cycle. When you take the water, it goes, and this is pseudo-saturation. We call it as a pseudo-saturation. So there is no saturation point here. So it goes as a steam. So it is not coming back as a water. Then the concept is that the mass flow rate through all heat transfer circuits from economizer inlet to superheater outlet is kept same. The mass flow is same, except at low loads. Where in recirculation is at low loads, I will explain, because this is the important thing. Up to this, from economizer to superheater outlet, it's a single flow. So it's once through, it doesn't come back. Okay? But the thing is that you can have once through boilers in subcritical mode also. But all supercritical boilers should be once through boilers. Understand that? Even in subcritical boilers, if I want to make it as a once through boiler, I can make it. I can see that the boiler takes the complete heat, the superheated duty also is made in the evaporator, and it becomes the once through boiler. Even a subcritical boiler can be made. The pressure can be less than critical pressure. But all these supercritical boilers has necessarily to be only once through boilers. We cannot bring it. The pressure has to be above the critical pressures. The critical pressure is 220 bar or 225 kg per self-cut gauge pressure. And the temperatures corresponding to that is 374 degrees centigrade. And the circulation system, if you see, a drum type boiler, economizer, it goes to a drum, and it will come back and have a circulation till you get the steam. And the steam is taken out for superheating and going up. But in case of economizer, so through, it goes up through the evaporator, through that it will go out. Only at lower load, till you establish, there will be a small circulation. Separator will be there. That is called the minimum once through load. That is up to some lower loads of 40% or 35%. You have to circulate it. Beyond that, it will be only once through. Thank you.
We can take I think
from on width side, because they have got assemblies. So it will clean and then move forward, and it can retract back. You will have mechanisms for that. That is called wrong retractable soot blowers. This is basically to remove the soot that is formed during operation.
Any more questions?
Any questions you can ask regarding boiler area?
Hello sir, I am Chandranayake from JJ College of Engineering.
Yes.
Sir, you said that coil has to withstand very high temperature.
Yes.
May I know what kind of material the material you use for the boiler to withstand such a high temperature? Is all the units are made up of the same material?
Good question. Actually, there are many materials. When you are the manufacturers or the standard scores, they specify the maximum temperature to which you can use those materials. If you go for ASME materials, mostly we are using ASME materials. For the areas like economizer and subcritical water walls, we use carbon steel, that is ASME, okay? And then SA 192 or 230. And when you go for the higher temperatures, you can have the T22, T11, T12, T22, T9. This group of things are called, may have 1 chrome half Mali or 1.5 chrome half Mali will be there. And then you can go for T91 materials, okay, which contains 9 chrome materials. These are all alloy steels. This T91 material can withstand up to 635 degrees centigrade as per IBR requirements and other requirements. But normally customers do not agree for that. They will ask us to restrict up to 600 degrees centigrade. Then you can have stainless steel. Okay, this stainless steel, we have got 347 or 347H stabilized stainless steel and 304. These are all the stainless steel materials which are used. And now, for very high temperatures like 596 degrees centigrade, when I say 596, This is the temperature of the medium and not the material. The material temperature will still be more because you are having a heat transfer. That will go up to 620 or 625. In those cases, we'll have to use Super 304H materials. This is a cold case material. This is called the ASME cold case material. Still, it has allowed us to use it. That's the only material available in the world now. That import it and use it.
Thank you.
Sir, is there any specific reason for hanging the boilers and the entire thermal system from the top, sir?
So, yes, as I told you in the beginning, you are having a very high temperature inside the boiler. Okay, the temperature will be around temperatures 1400 to 1500, and the hot gases are there. So all your materials will expand linearly. Lateral expansion, linear expansion will be there. You cannot restrict those expansions. To allow it to expand freely, you have to hang it from the top. So the structures. It's not possible to make any speech. No. Actually, what will happen? You will have a framework of a group of structures. So that will be tied, and then we'll have cross beams. From there, the total boiler as a total thing will be hung from the top. And wherever there is a medium flowing like pipes and all that, will have a support with springs. So it can expand even up to, for a 500 megawatt, the expansion can be up to 140 mm or 150 mm. Because for a height of something like 60-70 meters, we can expect an expansion of 140 to 150 mm. So that is to be taken care. So it has to expand downwards. That's why it is hung from the top. Small capacity boilers, we have bottom support. It is possible with rollers we can have bottom support.
From the earlier speaker, we learned that in India we are more on lignite-based coal versus anthracite, which is in the more developed nations. So are we disadvantaged? I mean, in terms of
No, in India we have only very few numbers of lignite-fired boilers because anthracite we don't have coal sources here. And as general thing is that the lignite has got a very high moisture. The lignite from NLC here, if you see that the moisture level is 50%. When you take it, you have to take it as a clay. Water will just fall. So the mill system, whatever I have told you, if you want to grind it, you have to make a beater mill. It's like keeping a hammer. That's called actually a hammer mill. You have to beat it and then grind it, and then it has to be processed. And for processing it, you cannot use hot air because huge amount of hot air will ignite the coal. So oxygen is there. So we'll have to take out some amount of gas from the furnace, put it into the mill, then dry it. So the system which is difficult, but then we have supplied for Neyveli earlier, and then we have supplied for Kutch lignite. So those things have been supplied, and even PCBS, the other section, the other type of boilers, we are using this lignite. Lignite can be fired, and for stoker-fired boilers, smaller amount of lignite is being also fired. So this is possible, but lignite as its availability is in Kutch and our NLC only. And when you come to anthracite, that type of coal is not available here. The mostly available coal here in India is subbituminous, and that too, the subbituminous coal is deteriorating, and then the ash content available is something like 35 to even 47%. The ash content is much more, and if you, for out of interest, that I would like to say that the ash content, the ash characteristics, you have to further go into that. The ash has got a cutting edge in Indian ash. It's not like other ash. It is not having a smoldering edge. It's a cutting edge. You have got aluminum oxide and silicon oxide. That's the basic thing, which is having the corrosive nature in ash. When it goes through, it will just cut the metal, in fact. So the continuous running of this will erode away the materials. So that way it has got another advantage about your soot blowers. It has got a self-cleaning effect. So that way it has to be comfortably used. That's why if you could see the boilers which are designed for Indian coal for the same capacity will be bigger. It is not because we do not know design. The thing is that it has to be conventionally and conservatively sized. If you are not conservatively sizing it, you will not have your boiler. It will be eaten away. That's why it has been sized like that. So that coal available in India is subbituminous mainly.
Good afternoon, sir. I am Badri from Jairam. Who is the largest producer of boilers, sir?
Where? In India or outside?
Around the world.
Huh?
Around the world.
Beijing is also one of the biggest producers of pilots. You can very proudly say in the world you can say that. And we got Shanghai Electric Company, Harbin, and MHI. Recently only these PGR and other people came very recently. So I got Alstom where we are having our collaborator. The CE was our earlier collaborator because the biggest manufacturer, and he had this technology very long back. He is our pioneer, that we follow them. And then for supercritical boilers we go with them. And steel industries, many boilers because Germans, Americans, and Japanese, Chinese, and Indians.
In amount they produce, you told that they used to produce in 800 megawatt like this. I'm asking.
See, you should take this into the world scenario. If you take that, actually, almost all the countries they have attained self-saturation. India and some of the countries are only we need power. That is power stations. If you could say like states, they have already reached self-sufficiency very long back. And China, they started very late and they have attained very fast. We cannot underestimate them. They have went very fast. And likewise, the market available, the word is Indian market, and of course from underdeveloped countries like Pakistan and Bangladesh and all other areas, and of course Middle East countries. Other than that, even the other areas of the world, all the Western countries. If you take German, France, everywhere they have completed their target. So they need not have to put their power plants, and that too many states they have got a lot of nuclear power plants rather than thermal power plants. Yes.
Thank you, Mr. Sitaraman. It was a very interesting question. But
Thank you.
But I would also like to tell the youngsters that India, even though we have very good technologists, we should acknowledge that in terms of technology, we are not the number one in the world. The intention behind the question was, what is the position of India with respect to the boilers that's being manufactured? Now, let me answer that question. If I am wrong, you can correct me. India is now going into supercritical mode. But in terms of advanced ultra supercritical, advanced supercritical, and IGC, the Western countries are far developed. They have much better technologies and technology, and we are surely lacking behind in some of the technologies. We are trying to catch up fast. So that is the challenge for the generation like you. And of course, as Sitaraman said, the problem is the Indian coal is a very special kind of coal, where the ash content is nearly 40%, and maybe in Germany and this thing, the kind of ash content would be 7% and less than 7%. So we have a special problem. We'll have to counter that. But in terms of technology, in terms of size, we are not the world leaders in terms of power generation, but we are one of the very important players. As he rightly said, the Western countries have plateaued. They have power generation. They have self-sufficiency in power. Like we have self-sufficiency in agriculture, they have self-sufficiency in power. For example, if you take the Tokyo city, it has 3 times load available readily for it. If you want 1000 megawatts, they have 3000 megawatts. Now in India, if you have 1000 megawatts, we have got only 60, 70 megawatts. And then the other point is that even though the Western countries have plateaued, each power plant has a life. Let us say 25 years or 20 years or 30 years or 40 years. After 40 years, you have to change the Indian power plant. So that is the other challenge. So we should admit that there are a lot of things that need to be done with respect to this thing, even though BHL is a Maharatna company and their technologies are wonderfully good. For example, I think fluidized bed boilers, whatever they have done, and nobody can match. We have leadership in certain areas, but overall leadership, the developed countries are more developed. Is that right?
Thank you. You're correct. Perfectly, you're correct. And then this supercritical boilers, now we have gone up to 800 megawatt. It's not only the megawatt, it is the temperature mix, this 568 and 596. As you asked the question about the materials, no? These materials have to be matched for the ultra supercritical. ultra supercritical we have to go up to 700 degrees centigrade. So we have to be prepared, first of all, to have the infrastructure, materials, everything. And still we are in the learning stage and R&D stage. We have got collaboration with Alstom, and then we have to further move on that. As you rightly said that we have to further move on that, and steps are being taken by BHEL to do ultra supercritical boilers, and the world has gone forward in these areas, and we are just trying to meet them. And of course, the boilers, even the shortest span of time, after getting the supercritical boiler technologies, that collaboration, we have now got an order of something like 17 boilers. For all the 17 boilers are being executed now, and this is one of the things which the chance for the other countries will not have that, because they have got a very big market, and that way global market is there. Here in India, we have got a good market, and we are proceeding towards that. So we have to do a lot more. Yes, the challenges are ahead of you. We have to do a lot more in that area. Okay. Anything else? Yes.
I have a question.
Yes, sir.
Actually, can you just tell us, it is slightly beyond the topic you are covering, but since you have a lot of knowledge and exposure in this whole thing, can you just highlight why we are not able to use renewable energy in terms of cost? What is the cost of renewable energy like solar, wind and other energies, and why we are dependent on it? In case you know.
To be very frank, I don't have much knowledge on that. To give such, because I don't have much knowledge on the other side of that, because the solar energy now, I read only through articles and papers that now Alstom they have made a trial of making some 200 megawatt with solar, which is the biggest one. And till such date we are doing in only 1 or 2 megawatts the same way. But I don't have much of an idea about why we are not doing and all that.
I think you are very, very safe. You will talk only when you know it 100%.
Yes.
But with my limited knowledge, I know that you will also know about it. Can you? I think that solar power, even though it is abundant in India, we can use solar power. The cost of solar power is maybe 4 or 5 times very unit cost, will be 4 or 5 times than the coal-fired ones. And the wind power is not available in all the seasons. So we are tied up with. We don't have any oil. We are importing oil. Even Gulf produce water, the energy from oil. But in India we have only coal-fired plant. Maybe, do you think that it is a correct statement?
Yes, you are right. Actually, in Gujarat, there is making a trial on that. Gujarat government, they are trying to make over the canal. They wanted to put these solar cells and then want to make a bit of solar energy. The initial cost is one, but nowadays the government is also prepared to invest on initial cost. The running cost will not be that much for a solar power plant. Running cost, see, when you make a coal-fired boiler, the coal cost is one. Then as I said, that 40% ash. How to send that ash out of that thermal power plant? How to dispose it is a very big problem. So those problems will not be there, and the emission problems also will not be there. And I think we have not made much of an advancement on renewable energy sources except for windmills. So that's what, with my knowledge, I know that. And as you said, rightly said, it is 4 times. Yes, it is 4 times costlier than what we do for thermal power plant. But that is not to be directly taken as a cost measure because of the initial cost. So for the running cost, you are not going to spend that much. It's very less.
So what is the quantity consumption of coal for 1 megawatt of electricity produced per plant?
It's $1 million question. Actually, when you take the consumption of coal per 1 megawatt, it has to be termed in terms of what is the calorific value of the coal. When you say the calorific value of coal is 3,000 kilocalories per kg, or 3,000 kilocalories, we can have coal from 2,500 to 6,000 kilocalories per kg. So it is the quality of the coal that is, what is that, approximately for a 500 megawatt boiler, if you say, it is something like 350 tons per hour with the 3,300 kilocalories per kg coal. So we can just calculate on that. Or we can say for 660 megawatt, it will be still less because it's a highly efficient rate. It will be something like 450 tons for a 660 megawatt. You can just calculate per megawatt with the 3,300 kilocalories per kg.
In the cost of producing, like power cost, what will be the percentage
give an idea that actually we've got as a heat rate, turbine heat rate. The total plant heat rate is something like 1,850 to 1,900 kilocalories per kilowatt hour. That is to make 1 unit, 1 kilowatt hour, you have to spend an energy of 1,860 to 1,900 kilocalories you have to spend. So that works out to something like half a kg to 600 grams of coal. We can calculate the cost. If the coal cost is going to be, we do not know exactly what the coal cost. If we can take it as a fuel cost alone, that will be the fuel cost. That will only the fuel cost. Then the conversion cost is there. So they can get. But normally now, for a megawatt, in the PPA, that is power purchase agreement, they go up to 2 rupees 75 paise to 3 rupees 75 paise, 4 rupees. That is the power purchase agreement between IPPs. They make it per unit.
Sir, one more.
Yes. Yes.
I think this can be the final.
Final.
Why we can use the hydrogen as a fuel in boiler?
We can use
Hydrogen is a fuel in boiler.
hydrogen as a fuel. So it's we do not know that, but because it's the burnables have to be there in the boiler. We know how to burn. We burn hydrogen also as a fossil fuel. In the fossil fuel, you have got carbon, hydrogen, sulfur. If you can develop a method of combustion for the hydrogen, that also can be used. So combustion is the major problem. You should know how to burn it, and then convert it into steam.
The easiest method, sir.
Huh?
The easiest or the cheapest method, sir. Easiest and the cheapest method for the fuel.
So I'm not getting it.
No, I understand what you say, but can it be standardized to the scale of operation that what we are talking of?
See,
You may be talking of smaller quantities that can be easily.
I will explain this. Actually, when you say a fuel, as Madam said, when you wanted to say, I told her something like 450 tons per hour. For every hour, you need 450 tons of coal to be fired in a boiler for getting a 660 megawatt. So, to that extent, when you wanted to fire, you have to get the fuel that is readily available. Readily available fuel for fossil fuels are coal, oil, and gas. So, gas, you have got various types of gases, oil, various types of oils, and other gas. So, there are certain coals and other fuels which we can handle also we have listed. These are all the outcome of some of the industries, like what I said, that bagasse, or when you say what do you call that, black liquor from paper industry. Those are all some of the items. So for these we have developed designs to fire it. In the case when you get hydrogen alone in abundant measure, definitely there will be an R&D project to make it fireable, and then we'll do it. Okay, now there is, as far as my knowledge, I am concerned, I do not know that things are to make it as a viable and what do you call that, as a business fuel.
I'm sure now you are also, aware of this. Hydrogen storage is a big challenge. There's a lot of research going on. So let's first learn how to store it and then learn how to fire it. So, okay, we'll talk about it offline. I'm sure we can
Only now that
take your
LPG is being
ideas.
fired actually. Only now LPG, in some small boilers they started firing it. So because it's costly, but then they have only the source of, only that source. You are actually liquefying the petroleum gas, which is not readily available. You are making it a process and then taking it. Normally at a bigger scale it will not be done.
I don't want to really discourage you, but we can always take whatever your inputs are offline. So we'll just break for tea. We can always meet over tea. Yeah? Thank you very much, sir.
Thank you.
Thank you for the really.
Thank you.